This jump demonstration will show how to use Monte-Carlo simulation to estimate response distributions under random variation in model inputs. We're using the tire tread data from the sample data library. This dataset includes 4 outcome measures: abrasion, modulus, elongation, and hardness, and 3 factors: silica, silane, and sulfur. Before we begin, we'll specify a spec limit for the purposes of demonstrating simulated defect rates. Let's set a lower spec limit of 500 for modulus. The tire tread data includes a table script for simultaneously fitting 4 response surface models, one for each of our 4 outcomes. At the bottom, the prediction profiler includes the ability to specify random variation in any or all of our 3 inputs, and use Monte-Carlo simulation to estimate the response distributions of each outcome under this variation. We'll go to the red triangle for the prediction profiler and select the simulator. We have the option to set each input as either fixed or random for the simulation. For any random input, we can specify the distribution type and associated parameters. We'll accept the default random normal distributions here, though in practice we'd match the distributions to realistic conditions as closely as possible. Down below, we have the option to add random noise to each of our outcomes. By default, JMP uses the root mean square error from each model as the standard deviation of the random noise. Finally, we'll set the number of runs to 5,000 and click the Simulate button. On the far right, we're presented with a simulated distribution for each outcome. Below that, we have the mean and standard deviation of each distribution, along with the defect rate for modulus, showing the proportion of simulated outcomes that fell below the lower spec limit of 500 that we set previously. If we'd like, we can simulate to a data table instead of inside the profiler, so that we can explore our results in more detail using JMP's other tools. Finally, note that more simulation options are available under the red triangle, including the ability to run a simulation experiment for the purposes of identifying optimal factor settings for minimizing defect rates.